In this video, we will learn how electric forces interact and what factors affect the strength of that electric force, called the Coulomb force. Let's begin by exploring the electric force surrounding individual charges and then around charges as they interact with each other. The electric field is the invisible area surrounding a charge where the electric force can be detected. We cannot see this field, but we can see how charges behave when in this field. Here we can see the electric field surrounding a positive charge. The arrows are drawn to go away from the positive charge. Here we have a negative charge. The arrows are drawn going towards the negative charge. When two negative charges are placed 0.75 meters apart, they repel, and the electric field lines do not intersect. The lines are drawn pointing towards the negatives. The same pattern is observed between two positive charges, but the arrows point away from the charges. When one positive charge is placed 0.75 meters apart from a negative charge, the charges attract, and the lines are drawn from the positive to the negative. This diagram summarizes all of the interactions we have seen. Here's what we've learned so far: the law of electric charges, which says opposite charges attract while like charges repel. We're now going to figure out what factors affect the strength of the electric force, called the Coulomb force. We'll begin by testing what effect the distance has on the force. Then we can figure out what effect the size of the charge has on the force. We will use a simulation to collect some data and then create a Coulomb force versus distance graph. We can then use that graph to figure out the relationship. Let's begin by setting the size of charge A, called QA, as 1 times 10 to the negative 4 coulombs, and the size of charge B, called QB, as 2 times 10 to the negative 4 coulombs. When the charges are 5 meters apart, the strength of the electric force between them is 7.2 newtons. Newton's third law says for every action force, there's an equal but opposite reaction force. So the force from A on B is the same as B on A, which is why they're both 7.2 newtons. We can put that number on our data table. Notice how the data table has the independent variable on the far left, the dependent variable on the far right, and the controlled variables in between. This allows us to easily make a comparison. We will make a comparison by keeping the size of the charges the same, but increasing the distance to 10 meters. The force is now 1.8 newtons. At a distance of 15 meters apart, the force is 0.8 newtons. 20 meters apart, it's 0.45 newtons. 30 meters apart, it is 0.2 newtons. And finally, 40 meters apart, the force is 0.11 newtons. Now we can make a comparison. As the distance increased, the strength of the Coulomb force decreased. And that is our conclusion. Let's plot this data on a Coulomb versus distance chart. The distance is the independent variable, which is why it's on the x-axis. The Coulomb force is the dependent variable. It's on the y-axis. We can clearly see, as the distance increases, the Coulomb force decreases, but it's not linear. It's actually an exponential decrease. Let's look at this change in more detail. As the distance doubled from 5 to 10 meters, the Coulomb force decreased from 7.2 newtons to 1.8 newtons. 1.8 divided by 7.2 is 1/4. So the Coulomb force is 1/4 as big when the distance is doubled. When the distance is tripled from 5 meters to 15 meters, the Coulomb force decreases from 7.2 newtons down to 0.8 newtons. 0.8 divided by 7.2 is 1/9. So the Coulomb force is 1/9 as big when the distance is tripled. When the distance is quadrupled from 5 to 20 meters, the Coulomb force decreases from 7.2 newtons down to 0.45 newtons. 0.45 divided by 7.2 is 1/16. So the Coulomb force is 1/16 as big when the distance is quadrupled. So putting all this together, we know that as the distance between the charges increases, the Coulomb force decreases, but it decreases exponentially. That's the square of the distance. If the distance is doubled, the force is 1/4 as big. If the distance is 10 times bigger, the force would be 1/100th as strong.